Well, thanks for coming to my talk. My name is Ameet Kini, and I'm going to be talking about simplifying change data capture using Delta Lakes. A bit about me, I manage our federal, I work at Databricks, and I manage our federal team of resident architects. This is a small team of elite Spark experts who are customer-facing, and we work closely with our clients, helping them onboard new use cases and ensuring that they're successful with Databricks. In prior life, I've been known to submit, contribute to open source. I had the pleasure of working in the open source geospatial community using a very early version of Spark way back when in the pre-structured days. And had a fun fact, almost spoke at Spark Summit in 2014. So you might be wondering, what does almost speak? So had a talk, submitted it, got it accepted, and then due to a work commitment, couldn't deliver it. So last minute handoff to a colleague, he gave the talk, and the rest is history. I forgot all about it. So a couple of nights ago when I was putting together these slides, I went on YouTube and saw if that talk still exists, and lo and behold, he actually decided to put a slide of me in his talk. So I actually thought about putting a slide of him in mine, but didn't. And then long time ago, I was had the honor of working at Google in the very early days of MapReduce. This was in 2006, before Hadoop. So this is the C++ version of MapReduce there. And then I did some kernel development at Oracle as well. It's a lot of structured and big data in my experience. So today, I want to take you through a journey of how we supported change data capture in the Databricks. And in this first half of the talk, there are lots of pretty architecture diagrams. The second half of the talk, I'm going to make it more developer track friendly. So this is targeted towards those who want to roll their sleeves up and diagnose and tune their change data capture use cases. And then throughout the talk, I'll be talking about new and upcoming features that you can go back and try out. So what is change data capture? At a very high level, it's simply put, it's just collecting a bunch of changes from one or more sources and merging it into one or more destinations. If you peek inside the data stack of an enterprise anytime in the last quarter century, you'll see a stack similar to the following. On the left, you have your sources, some of them structured, some unstructured. There is an ETL tool in the middle that transforms those sources and loads it into one or more warehouses. Informatica and Golden Gate have been around for a long time. And of late, there have been streaming platforms that look to make ETL more simple, basically allowing data engineers to add and modify their own pipelines. Enter Databricks. So back when I joined Databricks in 2017, the stack that you saw earlier looked kind of like this, where Databricks is a sink at the very end. So I had the pleasure of working with a federal customer who's here with us at the summit, where we productionized this exact stack to tens of data sources. And there, Informatica collected these sources frequently, many times a day, and loaded it into Oracle. And once a day, usually at night, a Spark job would ETL the changes from Oracle into the Databricks. So there were pros and cons with this architecture. On the plus side, it was very easy for someone to just in a couple of days go from never having used Databricks to loading a significant percentage of their enterprise data warehouse and having the data be ready to be queried at scale with Spark. There were some gotchas as well. Well, for one, there was a continued dependency on the enterprise data warehouse. And that went against the goal that our customers had. They wanted to sort of offload compute from the warehouse into the Databricks. Well, this didn't let that happen. The second is because these warehouses were already overloaded, we couldn't run the Spark jobs during the day when they were being used by their users. And because of concurrent read-write limitations in vanilla Parquet, we were constrained to run these Spark jobs in very short time windows at night, and as a result, the refresh rate in Databricks was at best nightly. So Delta was introduced in early 2018, and it dramatically simplified the stack for two reasons. So by then, nothing to do with Delta, but the ETL connectors, the ETL tool, had connectors that allowed them to write CDC records directly to cloud storage. And Delta had capabilities, which I'll be soon talking about, that allowed Spark jobs to read those changes from cloud storage and refresh tables in Databricks directly. The enterprise data warehouse did not have to be in this picture. So based on our experience deploying this at multiple clients, I wrote a blog in late 2018 describing how this can be done. Essentially, the summary is you have your CDC sources at the left. ETL tool is one of them, as we've seen. But you can also have vendor-supplied change tables, Oracle CDC, for example. Or you can have a poor man's change table using just insert, update, and delete triggers that are supported by most database vendors. And you get those CDC records in cloud storage. From there, Delta runs the following two-step SQL. The first SQL takes the raw records from cloud storage and does a simple insert into a Delta staging table. The second SQL reads the modified partitions of the staging table and overwrites those partitions from the final table. And we used two technologies that were introduced in Delta in early 2018. One of them was partition pruning, which was making sure that you only query those partitions that had changes from the prior run from the staging table. And a dynamic partition overwrite, which ensured that only those partitions that needed to be overwritten were doing so from the final table. So what worked? Well, the enterprise data warehouse was removed from the picture, and that let us refresh data in Databricks at unprecedented scale, speed, concurrency. You can have multiple of these running at the same time, and cost. However, there were still two major gotchas. For one, we relied on effective partitioning of the staging and the final table. And that required significant domain experience. Someone had to go in and really know the schema and the CDC patterns. And where there was no good partitioning column, the second step of overwriting the partitions effectively overwrote the entire table, which got very slow. So this brings us to Delta in 2019 and something called the extended merge. Now, merge has been around since the beginning of Delta. Expanded merge was introduced recently in Databricks Runtime 5.1 earlier this year, concurrently with Delta going GA. And it expanded the use of CDC to all three record types: inserts, updates, and deletes. So I'll step through this a little slowly. So this example was taken straight from this blog that we wrote earlier in the year. You've got a table of users that you're trying to merge into, call that your target table. And you've got changes in a source table. And these changes, well, so every record is a user, right? And every user has an address. And users frequently change addresses, and those are your updates. You sometimes have new users, those are inserts, and occasionally you may be asked to purge a bunch of users for various compliance reasons, those are your deletes. And the extended merge allowed us to support all three of these CDC record types. So, and the nice thing is, as typical of Spark API, what works in batch also works in streaming as well. So you can now do streaming merge into CDC use cases as well. So you can now go and try the extended merge into, but then we also used it under the hood to implement a new feature called MySQL replication, where you can have your MySQL tables synced up with Delta tables, and under the hood, it would run merge into to keep those two in sync. So going back to our CDC over Delta architecture, we went from keeping 2 copies of the target table, staging and final, and having to partition it, and having to potentially run expensive SQL, to just 1 copy and 1 merge into to do CDC. Visually, this is what it looks like. The changes are on the left. You can have inserts, updates, and deletes. The merge into would take those changes, map them to files in the target. That's the files 2, 4, and 8. It will figure out that the deletes map to those files, in this case 2, file 2. The updates map to files 4 and 8. And then it would override those files with new versions on the right, 10, 11, 12, in a transaction, and mark the old files stale. So with that, I'd like to wrap up the first section of the talk and move on to the second section, where you get to learn how to diagnose and tune your merge into commands. So at a high level, merge runs 2 joins under the hood. A join is between 2 tables. In this case, the join is between the source table that has the CDC changes and the target table that you're trying to merge into. So it runs 2 joins. The first join is an inner join between the source and target, and the goal there is to find the files from the target that needs to be modified. So in this case, it's files 2, 4, and 8. And the second join is an outer join between the source table and the output of the inner join. So those are that's in this case a join between the source table and files 2, 4, and 8. And the output of that is the mods to the target table, which is files 10, 11, and 12. Before we go further, I'd like to use a driving example, and I use the familiar TPC-DS schema. In particular, I'm using the store sales table, where every record is a sale made in an online store. And I've got, as my target table, a 100 million row store sales table that I'm trying to merge into. And on the left, I've got a 1,000 row source table with the same records that I'm merging into. And I do this merge, and as you can see, it's taking about 43 seconds in this case. And you may want to know, well, where are those 43 seconds going to? So you go to the Spark UI, and I wanted to show you how those 2 joins show up in the UI. They're not very intuitive. So the count at merge into command is the inner join, and the with new execution ID is the outer join. And as you can see in this case, the inner join is a fraction of the time of the outer join. And we'll go deeper into why that's the case and how to tune if something goes wrong. So if you'd like to know what the inner join, where those 7 seconds are going to, you would click on the count at merge into command, and you'll be taken to what's called as a query plan. Now, what I've done is I've taken the query plan for the inner join, and I've sort of magnified the section that's important here on the right. And you can see it's using something called the broadcast hash join. Now, there are multiple ways to run joins in Spark. Broadcast hash, as it turns out, is one of the fastest ways. It's not always applicable. It's only applicable when one side is small. And as it turns out, in CDC use cases where you're running merge, typically the source is small. So hence broadcast hash join. And the reason why it's fast is it's simply taking the small table and broadcasting it out to every worker that has a partition of the target table. So there's no need for shuffle and no need for sort. So if you find that your inner join is using broadcast hash, you're in great shape. And you might be wondering, well, that's broadcast hash. What else is out there? Well, there's something called sort merge. And sort merge, I had to force the optimizer to pick sort merge in this case. And you can see that it took 16 seconds, which is more than twice as slow as broadcast hash. And here's what sort merge looks like. Again, blowing up the relevant snippet here on the right. But right on top of the sort operands, there's something called the exchange. Let me see if I can point that out here. These two here. And what that's saying is that's shuffling both sides of the join. And it's because of the shuffle that the sort merge is slow. And that's avoided in the broadcast hash. So what's the takeaway from the inner join section? Well, if your CDC use case, your merge, looks like a typical one where one side is small, then ensure that it's using the broadcast hash join. And if you find that it's not using it, I wanted to show you a few ways that you can nudge the optimizer into picking broadcast hash. The first way is you can ensure that stats are collected on the join columns using the analyze table compute stats command. The second way is you can increase this parameter called auto broadcast join threshold, which basically says this is how large my small table can be before I stop picking broadcast hash. So in this case, the default value is 10 megs. If the source table is larger than 10 megs, it wouldn't pick broadcast hash. And if your table is, say, 12 megs, all you'd have to do is bump up this parameter to something more than 12 and have it get picked up. The third way is using optimizer hints. There's this broadcast hint that we introduced not too long ago. Unfortunately, the current version of merge does not use the hints. But I just wanted to put it out there because there is a general way to hint an optimizer to use a join algorithm, and it's the least disruptive way because you no longer have to collect stats on the columns or change a potentially global Spark conf parameter. You just hint the exact query you want to effect, and have it take effect. So that's the inner join. Recall that merge runs two joins. The second one is outer. And the goal in the outer is to write out the mods to the target table. And as you can guess, its latency is tied to the amount of time it takes to write to cloud storage. So in this example, we're writing 3 files out. The time it takes for the outer join is bounded by the time it takes to write those files out, though that's the dominant time. Now, later on, you'll learn that it's writing more than 3 files, but for now, let's keep it simple. I wanted to show you an example that shows how tightly outer join and merge is tied to the cloud storage write time. So I've done a simple experiment here. I've taken the familiar 100 million row store sales table, and I've neatly packed it into 5 1 gig files. So I basically ran the delta optimize command, which packs it into 1 gig files. And I'm running the merge command 3 times. And in each case, I touch a varying number of files, right? So in the bottom left case, I'm running 1,000 rows. And in all 3 cases, it's merging 1,000 rows into 100 million rows. But the bottom left case, as you can see, it tells you how many files are being touched. It's touching 1 file, 1 out of 5. In the middle case, I'm touching 3 out of 5 files. And in this case, I'm touching all 5 of those files, 100% of the data. And here are the results. Purple is outer join, blue is inner. And as you can see, the overall merge and outer join time is directly affected by how many files are being touched. The inner join, on the other hand, is a small and unchanging portion of the overall time. So merge creates a lot of small files, and I wanted to show you how many. So here what I'm doing is I'm running the merge command, the same one on the 100 million row packed into 5 files. I take a pulse of the directory, do a directory listing prior to the command, and it's kind of hard to say, but it says that it's 5. So there are 5 files, which we expect. We run the merge command. I run a vacuum to clean up the stale files, and I do another directory listing. And as you can see, it's a lot more than 3. It's actually 202 files. So you might be wondering why 202? It's because of the Spark SQL shuffle partitions parameter. Anyone who's done Spark SQL joins would recognize this parameter. It controls the number of shuffle files. Well, we're running an outer join here. It's bound by that same parameter. And if you're wondering why 202, well, we started out with 5 files. Merge figured out that it needs to change 3 files, so 5 minus 2 minus 3 equals 2, plus generated 200 new files. So that's 5 minus 3 plus 200 new files. So outer joins are fast as the files get smaller. And I wanted to show you by how much. So here, focus on the first 2 bars here. Again, I'm merging 1,000 rows in both cases, and I'm touching 1 file. But in the left case, I'm touching a fairly small file, and in the right, a fairly large file. And as you can see, in the small file case, it's it's twice as fast. So merge is fast on small files. And the reasonable conclusion from that is, well, maybe we should have just lots of small files. And at this point, you might be wondering, how is it that I'm at a big data talk and somebody's saying small files are good for you? Well, it's good for merge. It actually is. But it affects your queries. Right? So queries get slow with small files. And I wanted to show you how bad it can get. So on the left, in both cases, I'm running the query twice. On the left, it's the old 100 million row packed into 5 1 gig files. And on the right, it's the 100 million row in 1,355 files. Basically, I never ran optimize. And as you can see, the same query takes 10 times as long on the small file case. So the old adage that small files are bad is still true. And you can see the scan operator at the very top tells you how many files it's picked up. So optimize is your friend. Until now, it compacted files into 1 gigabyte files each. And there are a couple of issues here that I wanted to point out. The first is that it can be pretty slow to coalesce and compact your files into 1 gigabyte chunks. The reduce phase has to do a lot of work. So optimize can be slow. The other is a bigger dilemma that data engineers face with CDC and merge, which is, you've got large files which are great for queries, but not for merge. And as you saw in 2 slides ago, small files are great for merge, but not for queries. So do we have to deal with this trade-off? Now, as it turns out, Delta allows you to control when and where to optimize. By that, I mean, if your merge patterns are such that the merge changes frequently hit a small and consistent portion of the overall table, call that your hot section. You can choose to keep your hot section in small files and optimize your cold section. But the scheme is pretty fragile in the sense that if your merge patterns change or if your query SLAs change, then this sort of breaks down. And the recurring theme in my talk, as you might have caught, is that anytime you find something painful in CDC, we end up fixing it in a couple of releases. So for example, the Delta solved the nightly refresh rate problem by reducing the dependency on the warehouse. The expanded merge resolved the pain of having to keep 2 copies of a target table, having to partition it, and run potentially expensive inserts. And now with this next feature, data engineers can run fast merges and at the same time not slow down their query workloads, something called auto-optimize. Auto-optimize is available as of 5.3, and it has 2 smarts that allow the data engineer to not worry about when and where to optimize. The first one is adaptive shuffling, which controls the number and size of files written out. So you no longer have to hard code the Spark SQL shuffle partitions. It figures out how much data it's writing out, and it controls the number of shuffle files accordingly. The second is after it writes out the files, it triggers a faster and cheaper version of Optimize that collects the data into 128 megs chunks. You might be wondering why 128 megs? Well, we figured out that the sweet spot of running a fairly fast Optimize, but at the same time not having too many small files, is around 128 megs. Anything larger than that, and Optimize itself slows down. Anything smaller than that, and you've got a lot of small files. So it's private preview in 5.3. If you'd like to use it, please contact your local Databricks rep. And with that, I'd like to wrap up my journey of supporting CDC in Databricks Delta. So use merge into to perform CDC into Delta Lakes. It provides a unified API for both batch and streaming. There are a number of performance enhancements in the Delta Lakes, and we continue to add to it in each release that speeds up CDC and merge into in particular. And one can never overstate the importance of reliability when doing ETL, CDC, or otherwise. And Delta goes to great extents to provide a reliable storage layer on top of cloud storage. If you find yourself rolling your sleeves and diagnosing and tuning merge into, recall that it runs 2 joins. Ensure that your inner join, if it meets the criteria of small and large, it uses broadcast hash join. And the outer join, if you recall, is bound to the amount of data that's written out to cloud storage. Consider using auto optimize to tune your to make sure that your merge runs fast, but at the same time not slowing down your queries. I'd like to put in a couple of plugs to talks that go into things that are discussed in the previous slides. So Burak, who was here just before my slot, is the one who wrote Auto Optimize. He's going to be touching upon it in his talk. It was earlier today, so please catch the video. Daniel Tomes is giving a 2-part deep dive into optimization in general tomorrow. And then my colleagues Joe, Stephen, and Burak are putting together a tutorial on how to build robust production pipelines with Delta Lakes. That's all I had, folks. Can I take questions? Yeah. Can you use the mic, please? Sure. So we can hear it. Yeah.
So is there currently, or are there plans in the future to include any Bloom filters or bucketing to allow for better map side joins or things like that? Any kind of indexing that's going to be included?
Yes, that's a great question. So is there planned support for Bloom filters and bucketing for doing the map side joins? Bloom filters, yes. Bucketing, let's talk more offline, but bucketing, as it turns out, is possible to do map side joins without doing bucketing. We found out that bucketing is great, but it also constrains scan time because the number of threads that are spawned for doing the scans are now limited by the number of buckets. Any other question, folks? I'll hang around. Yes, please.
You mentioned about the 2 joins happening when the merge happens.
Yes.
Both of them include the source dataset. Is there a benefit of persisting the source dataset just before the merge?
Okay, is there the benefit for persisting the source data set just before the merge because we're using it twice? So let me see if, so yes and no. So the examples that I use, it is materialized as a table. In the Databricks, if you're using the Databricks, we keep a cache on each instance called the DBIO cache or Parquet cache. You can read about it in the docs. What happens is when you run the first join, it automatically caches the source table. Now, the source table frequently is very small, 1,000 rows, maybe 10,000 rows. But even otherwise, it is cached. So the second join picks up the cache version.
So the fifth strength of Delta that they talked about is time travel. Does time travel require any specific optimization techniques? Does this apply just equally well when you're doing time travel? Or is there anything specific that you'd want to do to enable very optimal time travel?
So I didn't catch the second part of the question. The first part was for time travel. Are there any performance enhancements that we use for time travel? Okay. The time travel basically is, you can query your data as of a certain time. Now, as it turns out, we in Delta we keep a metadata listing of files as of a certain time. And when we query, when we pose a query that has a timestamp, what we do is we go into the metadata listing and find the files that satisfy that particular time and go directly to those files. That becomes the sort of snapshot that we're querying. So we rely on metadata listing. We rely on fast metadata listing provided by the storage layer. We also there was something else that I was going to say that I lost my stream of thought there. But yes, so those are the main enhancements that we use in Delta for supporting time travel. Did I answer the full question? I'm not sure if I caught the entire one.
That answers it. Just are there any special optimization approaches that you can use if you want to improve your time travel performance? Or does, I mean, I haven't used it, so does time travel just work very quickly and easily no matter what, or do you have to also optimize time travel?
No, it works right out of the box. Now, you can always partition your table and ensure that there are min-max stats. You can use Z ordering along with time travel, but just to use time travel, it works right out of the box. Now, what I was going to say was it came back to me. Time travel only works if you haven't run vacuum to clean up those files. So there is that constraint. Make sure that you haven't vacuumed those files already. All right. Thanks, folks. I'm going to stick around for a bit.